Hello, everyone, and welcome to Klara's latest webinar, OpenZFS Data Replication. So let's get started. Quickly going through our agenda for today, we'll start with introductions of myself and our co-host. Then we'll talk about what ZFS replication is and the basics of how to start using it. And then we'll talk about some of the tools you can use to make it much easier. Then we'll talk about using delegated permissions so that you can do replication without requiring administrator privileges. And we'll also talk about a common request about resuming replication, what happens if the internet connection that you're replicating across is interrupted. Then we'll also talk about other ways to apply replication for things beyond just backup and replication, but also how to use it for improved data mobility. Then we'll answer some more questions from the audience, and we'll go from there. So starting with introductions, hi, I'm your host, Allan and Jude. I'm the CTO and co-founder of Klara, and I'm joined today by Jim Salter.
Hi, everybody. Those of you who know me may know me as Mercenary Sysadmin. I've been around the web all over the place talking about ZFS under that nick, or you may have seen some of my old articles at Ars Technica or elsewhere, including right here at Klara Systems.
Yeah, Jim's written a lot of articles about ZFS and replication and so on our website. Head over to klarasystems.com/articles and check that out.
I should probably mention you may also know me as the original author and developer of the Sanoid and syncoid tools for ZFS.
Yes, which is part of the reason why we brought Jim in to talk about how those tools make these basic concepts we're going to talk about much easier to implement. So to get us started, let's talk about what actually is replication. So what ZFS replication is doing is being able to serialize a file system, and we'll talk about what that actually means. So when you serialize an object in data science or computer programming, it's generally about making it in a format that can be transported easily and interpreted by the other side where things might not be exactly the same. So in this case, it allows us to encode the contents of the file system in such a way that we can recreate that file system on the other side, even if there are changes along the way. So this allows us to cross operating systems. So it doesn't matter if your source is FreeBSD and your destination is Linux or Lumos or Windows or Mac or whatever, and even allows us to cross endianness. So you can send from an x86 machine and receive it on PowerPC, or go from ARM to RISC-V and any other platform differences that most file systems can't handle. Because ZFS replication will serialize the data, it puts it in a format, which we'll show in a minute, that makes it easy to interpret on the other side and recreate the file system exactly the same, but without depending on it being byte for byte the same. This also provides forwards and backwards compatibility. The fact that you can make a ZFS send stream with the latest version of ZFS and still receive it with a 10-year-old version of ZFS, or vice versa, really shows the power of being able to serialize the file system. Another important thing about the way this works in ZFS replication is that it's unidirectional. So the sender controls everything. They will package up the file system into the serialized format and send it. And it doesn't require any interaction with the side that's going to receive it, which means you don't have to receive it right now. You can do a ZFS send stream and write it out to tape and only receive it a year later into another machine or whatever. It allows ZFS replication to not depend on actually communicating with the other side. And that also helps with that backwards compatibility because we don't have to negotiate with the other side what is supported. The serialized format ensures that we dumb the data down into something that can be supported. The other interesting thing about the way this works is that it doesn't require special handling for things like permissions, ACLs, extended attributes, and anything else that might be attached to the file system. All of it is just data that gets serialized the same way as the contents of the files. And so ZFS doesn't have to do extra checks or do any extra work. It just sends the data and the other side is responsible for interpreting it. So if you use some of the ZFS debugging tools, we can actually see what is inside a send stream. But basically, it's an object command that says we need to create a new object. It's this number, this type, and it contains this data. And then we can free anything. So if the object was using space, so if you're doing like a incremental replication and modifying an existing object, you can say, you know, this part of it is now free space. And then we have write commands that say, you know, at this object, we're setting its checksum as this and its compression is that. And we say, you know, at this offset of 1 megabyte, we've made a change for 4 kilobytes of data. And then at another offset, another 4 kilobytes. And we just send the blocks that actually changed. This allows ZFS to be able to send the differences between two snapshots without ever having to know even which part of it are files and which part of it changes to the directory or permissions, or what changes are just to extended attributes. All of it is just data that it can collect and send very quickly. And that's what makes replication such a strong method for serializing data and moving it to another place. So as we start to talk about actually using replication, we want to start by defining some terminology we'll be using throughout the presentation.
So recovery point objective, RPO, is a term that any system administrator should be very familiar with, and unfortunately very few are. This is a really great way to talk to business folks, by the way. Your RPO is, as it says on the slide, how much new data will be lost by reverting to the backup. And this is controlled by your backup frequency and duration. This is probably the simplest thing and the first thing most people think about in terms of backup schemes. If I have to go back to backup, how much data will I have lost because of how much time it's been since the last time that I backed up? Now, our next term is not thought about frequently enough, in my opinion, particularly by graybeards, such as myself, the recovery time objective. Back in the 90s, when I first got my serious professional start to being a sysadmin, nobody really thought much about recovery time objective, because if your system crashed, most employees could find other things to do in any given business while the computers were down. They weren't necessarily that universally essential yet. But the other thing was, you know, generally your business owners were just so happy to have everything back eventually that they weren't going to kick up too much of a fuss about how long it took to get it restored, as long as it came back at all. Well, that's not the case anymore. Most businesses, if the computers are down, nothing more useful than sweeping the floor is happening. So your recovery time objective, in many cases, has actually become more, not less important than your recovery point objective. There are an awful lot of business owners out there now who will say, you know, if I can't have all of my data back the way that it was, fine, I can live with that, but you've got to get the system back up so I can do new things now. So, recovery time objective, how long does it take to finish restoring the data from the backup and get everything actually usable for the users again? Now, in part, this will obviously be determined by the amount of data that you have to restore and how quickly that data can be moved from your backup device to production. But the nice thing about ZFS replication is that actually that pretty much is the whole RTO. How much data do you have, and how quick is the transport to get it back, and how quickly can you actually barf those blocks back down onto the disks? That's pretty much the whole thing. But for backup systems in general, there tend to be a lot of other things that can drastically slow down your recovery time. For example, if you're working with tapes, you've got to spend an awful lot of time mounting the tape, cataloging the tape before you can even begin trying to recover actual data. And in many cases, the data that you recover won't already be in the format that you need. The other nice thing about recovering by replication is the entire process leaves you with a usable system, period. There's not like a bunch of separate stages that have to go in order. On the other hand, if you're recovering from a tape, you're probably going to be recovering either a tarball or something very similar to a tarball. So you first have to mount the tape, then you have to catalog it to find out how many tarballs are there, figure out which tarball you want. Then you got to get the tarball off the tape, and you've got to decompress it and recreate the original format of the data. All those things have to happen before your users can actually get back to working again. Whereas with replication, depending on the severity, either a full replication and then you're good to go, or in a lot of cases, if you're talking about, something more along the lines of like somebody made a catastrophic error that needs to be corrected by, a rollback or a replication in from offsite or from onsite hot spare, it may literally just be seconds to your recovery time objective if a simple incremental is all it takes to get you back where you need to be.
Yep. So from the ZFS side, we have some other terminology to look at. First is a snapshot. This is basically a point-in-time view of a file system. So in ZFS, snapshots can be created instantaneously, and they are exactly how that file system was at that transaction group where the snapshot was created. And it provides a consistent view of the file system at that specific moment. So what that means is one problem with the traditional file system, especially when doing backups, is that if you're backing up the files by walking through the directory and doing one file at a time, if a file changes after you've already passed it, you don't catch that. But also, if a related file later in the list changes, then you end up with the first file from before the change and the second file from after the change. And now the two files don't match up. And if it's a database, that's not going to work very well. And so by using snapshots as the source of our backup, we're ensuring that we have our backup is of the same of all the files at exactly the same second across the entire system, rather than each file being backed up at the time it was backed up at. And that gives you a much better source for your backup and a much better recovery stage, because you don't have to worry about different files being from different times, because your entire backup is of this snapshot. And that's why snapshots are the basis of ZFS replication. And then there's replication itself, which is serializing the file system, which we've kind of already talked about. But now that we have that terminology out of the way, we actually have our first question. So Chris asks, it'd be great to explore snapshot rollback and the potential consequences in a replication setup, especially if somehow it was malicious or accidental. What steps could you take to prevent permanent data loss on both systems? So it depends on what you're talking about. If your file system was rolled back to an older snapshot on one side, you can always reverse the replication and restore the newer snapshots from the other side to the first. So if it got damaged on the source, you can replicate them back from the backup and just basically incrementally replicate from the last snapshot that is in common up to the newer one and undo the rollback. Or if it was just the backup that got damaged, then you can just re-replicate just the snapshots you're missing and get it caught back up. But if you want to prevent that, ZFS has a feature called a hold, where you can basically tag a snapshot saying, I need this snapshot for whatever reason. You can basically put a little tag on it with information, and that snapshot cannot be deleted until that tag is manually removed to say, okay, I'm done with this. It's like a lockout tag when working on physical machinery, where you might be, my arm's going to be inside this machine. I don't want somebody to power it on while my arm is in there. So I've locked out the power button so that nobody can turn it on. Snapshot holds work basically the same way. You can prevent someone from deleting the snapshot because you're using it. It can be especially useful when your snapshot aging out is automatic and you want to prevent one snapshot from being aged out because you still need it for some specific case.
For those of you old enough to remember floppy disks, remember the little write protect tab? That is essentially what ZFS hold is for a snapshot. Now, the other thing that we probably ought to cover, particularly given that Chris was talking about, accidental and or malicious rollbacks, I can speak to that from unfortunate experience. A client of mine once briefly hired an IT person who ended up not being the best choice for that role. And at one point, that IT person did a really, really interesting thing, because at that particular client site, all of the production virtual machines, which everything is on ZFS, of course, all the production virtual machines had been created by replicating gold images into a new production copy, and then from there, working all along the lines. Now, unfortunately, what we didn't do when we created those production images by replicating from gold is we didn't actually delete the original snapshot that replicated from the gold image to begin with. That meant that there was still a common snapshot. The very oldest gold snapshot was common in between the gold image and the production image. Now, this, not necessarily the best choice for the role IT person, one day decided for some reason, and I cannot tell you why he thought this was a good idea, he actually replicated from a gold image onto a production image, and by doing so, just rolled it all the way back, permanently destroying all that data on the production side. Making things even worse, he didn't tell anybody that he had done something dull. And by the time I found out about the problem, when the owner of the company reached out to me later, it was only a couple of hours away from his boneheaded mistake not only having been replicated from production where he messed it up to the on-site hot spare, which gets automated replication every hour. We were only a couple hours away from it replicating offsite to the offsite disaster recovery that only gets daily replication every 24 hours. And if that had happened, it would have permanently destroyed all the data in all three places.
Yeah, I had a similar anecdote from another place where, while trying to increase the size of a ZVol, they made a typo and resized the ZVol on a different pool. So instead of doubling the size of the ZVol on the SSD pool, they cut the size of the ZVol in the hard drive pool from 100 terabytes to 20 terabytes, therefore
Ooh.
deleting 80 terabytes of data. It took a while to restore that from backup. So Chris had a quick follow-up to his question. He says, he means if you accidentally roll back a snapshot and then replication runs and removes the older snapshot from the replica machine.
Which
So
is exactly the
ZFS
scenario I was talking about, actually.
Right. By default, ZFS will not work there. It will actually refuse on the receive side will refuse to receive the thing saying the receive side is newer or has changed since what you're trying to replicate, and it won't let it go forward. But most replication tools will use the force flag to keep it going because they need to be able to support that. Because if you rolled it back on purpose, then you need it to do that and continue to back up.
Not just if you rolled it back on purpose, even
Mhm.
more commonly, most people's backups are mounted in anything, even something as simple as LSing the mounted directory of a replicated file system. That's enough to constitute a change. You'll update A times in that, and that means new blocks have been written. And that means without the -F flag for force, incoming receive will not function. It will just error out. So without using -F for force, the unfortunate reality is in most environments, replication would fail nearly every time.
Yeah. So again, holds and kind of almost related to Jim's thing of keeping some snapshots in common by using a hold on each side, ensuring that they don't go back too far means that you'll always have something in common. Okay, so now that we have the terminology out of the way, let's actually look at how replication works.
Actually, before we move on, if there's anybody out there who's like really kind of mystified as to how snapshots actually work, can you just raise your hand real quick with the tool and we can give you a quick answer? Okay, good. Not seeing any
Yeah,
raised hands, but I wanted to make sure because I remember
yeah,
that
and if
how
you're
brain breaking they were.
if you're too shy, the Jim wrote a great article about how snapshots work on the Klara website, and you can go look at that later.
Okay, so let's talk about the bare basics of replicating a file system. Absolutely no bells and whistles. The simplest possible way to do it. As we've discussed, we're talking about block, not file level stuff, and everything is snapshot based. If you haven't taken a snapshot, you literally can't replicate because that is what you are replicating. Now, that was a source of some confusion for me when I was first, getting used to these concepts many, many moons ago. So, just to answer some questions that some folks might have, you're actually replicating a snapshot, which doesn't change the fact that you do also have a live file system on the target. Your live file system is equivalent to the most recent snapshot immediately after a fresh replication. And then if you do anything to it, those changes are built on and become part of the live file system. Although, of course, they don't change the contents of that last snapshot that was replicated in because snapshots are immutable. So, in order to replicate, assuming we have a pool named pool and a data set named set, we first take a snapshot. ZFS snap pool/set @1. @1 is the name of the snapshot that we just took. And now we need to pipe from ZFS send to ZFS receive. And again, this is the simplest possible. What we're looking at here is literally just replicating on the same machine. So we ZFS send pool set @1 and pipe that to ZFS receive pool new set. And once that's done, at pool new set, we will have the entire contents of pool set as they were when the @1 snapshot was taken.
Yeah, and that a snapshot named @1 will exist in pool/new set as well.
Go ahead and move to the next slide.
Already did.
Oh, duh. So yeah, and that @1, that is your common snapshot between your source and your target. As long as you have at least one common snapshot, you can do incremental replication, which is where the magic really happens, in my opinion. So example here, we take another snapshot named @2 on our source pool set. Now as ZFS send with the -I flag for incremental, the capital I version means I want all of the snapshots in between my common snapshot and my newest snapshot. If you're to use a lowercase I there instead, you would only get the second argument. So when we say ZFS send -I pool set @1 pool set @2, we're saying I want to make sure that I've got the snapshot @2 and any other snapshots in between @1 and @2. Um, I want those to be received at pool new set. Now, that's not going to take very long at all because unlike other tools you might be familiar with, such as rsync, note that we already know what ZFS send does, and it doesn't need to talk to the other side to do it. So there's not any groveling over file systems to figure out what blocks might or might not have changed. It already knows because it knows I'm sending snapshot 2. And this being an incremental, it knows, well, I just need to know the difference between what's in @1 because I know the other side has it and what's in @2. So essentially, we're just sending a patch set. And we don't have to figure out how to build the patch set. We already know because we've already got those two snapshots to work from.
Yeah, basically ZFS keeps what's called a birth time, basically the transaction group when a block was written for every single block in the file system. And so when you're doing incremental between @1 and @2, it just says every block born in this range, I'm going to need to send to the other side. I don't need to know if that's a file or a directory that changed, or somebody ran chmod on a file, or added new extended attributes, or changed an ACL. Doesn't matter. Just every block that has a birth time between @1 and @2 needs to be serialized and sent to the other side, and that side already has @1, so we'll be able to just apply these changes on top and have @2 without having to even look at what's in @1. And that's what makes it sometimes thousands of times faster than a regular backup or a tool like rsync.
And it can do that because from ZFS Send's perspective, it's all the same. Blocks are blocks are blocks. It doesn't
Yep.
know, it doesn't care, it doesn't want to know or care what's metadata, what's data, what's a file that you think is really important or not really. It's nope, it's just all blocks. Just barf them down the wire. That's it. All right, so now let's talk about raw send. If your source data set is ZFS encrypted, you can replicate it to a remote untrusted system without exposing the key, which is really neat. Now, by doing this, that means that you can set up a backup target at some place that you don't entirely trust. The most common example would be a public data center. And you might say, well, I don't really have any way of verifying whether the employees of this data center, maybe one of them is a rogue and might wander around looking for interesting data to mess with. Or maybe I don't entirely trust, the management of this place or a network in between or what have you. If you're doing a raw send, you never actually send decrypted data at all. So even if you're worried that somebody on the road end might be messing around using root level privilege on that machine, it's not going to do them any good. So taking a look at how that works, we take a snapshot, ZFS snap pool set it to. We do the same ZFS send incremental, but we just add a new argument, -W. -W is the argument that specifies a raw send, and that means send this block exactly as is. If it's compressed, it stays compressed over the wire. If it's encrypted, it stays encrypted over the wire. We're not doing anything to it. Whereas normally, without the -W flag, compressed blocks get decompressed before they're sent, unless you use a different argument for that. Encrypted blocks would get decrypted prior to getting sent, and all this kind of thing. And then on the other end, some of those properties might get changed again based on the properties of the receiving data set. But essentially, you're looking at decompressing, decrypting, all that, and -W keeps that from happening. Like we said, even with root access on the other side, you don't have to worry about somebody getting access to that data. Now, if you got root on the other end, you can delete it, but you can't actually tell what it is. And you can't monkey with it usefully, for one thing, because you can't tell what you're doing if you monkey with the data. And for another, because ZFS will immediately see, hey, these blocks don't match their checksums. This is crap. I'm going to restore that from redundancy or parity. Chris says, again, big debate I often have with people, is replication to another system a backup? Yes, that is absolutely a backup. It is unquestionably a backup. I cannot imagine why you would say it isn't a backup. The only bad thing that you can say about using replication as your sole source of backups is that means that if there is a really nasty bug in the code for ZFS itself, particularly in the ZFS send or ZFS receive sides, it means that no matter how many backups you have, they might all be corrupt if the reason for that is a bug in the replication code itself. Other than that, no, there's nothing functionally different between replication and any other form of backing up. If you would consider rsync a backup, you certainly should consider replication a backup.
Yeah, for sure. It's basically, if yeah, ZFS replication is going to provide a more consistent backup than most of the other tools. And again, because it's based on snapshots, it also means the replica is not just a copy of the data, but actually all of the snapshots. So you can choose to restore from any one of them, because kind of related to the discussion of the recovery point objective, sometimes it turns out it's like, yeah, our newest backup is from last night. But it turns out the ransomware got in the night before. And so we actually need to roll back further to get all the data back. And being able to do that, or being able to pick and choose files from both, gives you a lot more flexibility than most other backup systems.
It's also really hard, in my opinion, to overestimate the value of the backups on the remote system being already assembled, intact, ready for use, inspection, and everything. There is an enormous difference between being able to dive directly into the data on your backup system versus staring at several 30 terabyte tar balls and being like, well, I guess we can get started, and we'll hope that what we want is in there once we're done.
Yeah, like we can talk about maybe later. Your replica could be set up so that if something takes out the primary system, the replica can just start up the VMs, accessing those files, and you're back up and running in a couple of minutes instead of waiting for 30 terabytes of data to get rewritten to a hard drive.
Yep. As a matter of fact, if you'll remember the war story I told about the client who hired a not so great IT person who completely screwed up their production and waited long enough to talk to anybody about it, that the hot spare was also screwed up, and we only had a couple hours left before he would have knocked out the offsite disaster recovery. That was a very large amount of data. It was an enterprise. It was an enterprise, all-in-one kind of a system managing the entire workflow for the whole, like, I think 60 site enterprise. And we would have been looking at a ton of downtime if we had to, even with replication, move all the data back across the country to the production site and go from there. So what I ended up doing is I actually promoted the disaster recovery side to be production for that particular VM, and just spun up the VM on that side directly from the backup and began replicating from that disaster recovery site back to the normal production site while they were up and running on the DR site. Now, the actual replication back, due to the amount of the data versus the amount of bandwidth that they had, took nearly a week to complete, but they were up and running for that whole week instead of panicking or trying to drive a station wagon with hard drives stuck in the back across several states.
Yeah, you really can't underestimate the value of the backup being a usable file system rather than just a backup.
Michael asks, so would you consider ZFS replication a complete replacement for traditional backups or an addition to them, i.e., does it cover all the same cases? Well, there is only one case that ZFS replication doesn't cover, and that case is there is a catastrophic bug in the file system itself. The only way that a backup can truly protect you entirely from that is if you're backing up onto a completely separate file system, therefore getting your data out of the clutches of the file system that might have had the bug that would have eaten all the data. ZFS replication can't do that for what should be fairly obvious reasons. With that said, if you were using something like, I don't know, anything from rclone to Snapshot to Borg to, Windows backup to you name it. If you're not crossing file system boundaries with those tools, you have the same problem with your backups with those very traditional conventional tools. The other thing I'll mention is that in cases where you literally just can't afford an old school traditional backup because you have too great a volume of data that's changing too rapidly, to be able to manage that with the transport throughput that you've got available, you can kind of mitigate the issues with that to a degree with a staggered setup, like what I mentioned before. Most of my clients will have a production server, an on-site hot spare server that gets hourly replication, and an off-site disaster recovery that gets daily replication. So that gives you an extra window in time. If you have a catastrophic file system bug that crops up and eats all your data in production, and your production has replicated a hot spare and therefore it ate all your data there, you have some time before it gets to the DR side. This is essentially, again, the exact same issue as what I had with my catastrophically corrupt local IT person.
Yeah, and like any backup, you do still need to test and make sure you can restore. But ZFS, is going 20 years and not having these problems. So we're pretty confident it's the right solution for this. But you can also, to Jim's point of the staggered thing, create a traditional backup from the replica if that's what you're after, making sure that you have a copy, but not having to have it cause the additional performance load on your primary systems.
Yep. All right. So if your brain is spinning a little bit and you're like, oh, wow, I got to take snapshots. I got to figure out what my common snapshot is. And then I can think about replication. We haven't even talked about adding SSH into the mix. If I want to leave the machine, this is looking like more of a pain in the butt than I want to bother with when rsync or whatever other tool is so easy. Well, don't worry about that. We just showed you literally the most basic way to do it with nothing but ZFS commands themselves. However, there are a bunch of orchestration tools out there that make replication a whole lot easier. You can argue I'm biased, but I happen to think the best of them is my own tool, syncoid, which I'm showcasing here. So if you really love the way rsync works and feels, syncoid is absolutely the tool for you, because just all you need is syncoid source target. You don't have to tell syncoid, is this, a local or a remote, do I need this, that, the other? It figures it all out. Now, in this example, we just see, again, a local replication, syncoid pool image to pool image copy. But we could just as easily said syncoid pool image root at other box : pool image copy, and it would work the exact same way. Whether you need a full replication or an incremental replication, syncoid figures that out on its own and does all those things for you. And so that makes this automatable in a way that just bare ZFS replication really isn't, because it doesn't sound like too much when you first think about it. Okay, I got to find a common snapshot, and then I got to replicate from the common snapshot to the newest one. That doesn't sound so bad until you start thinking about trying to do it in a cron job. And trust me, it gets really bad at that point, which is why I built this tool to begin with. Now, there are others out there, but I think that Sanoid and syncoid are probably the most full-featured out there, and they have been very reliable for an awful lot of people for something like 7 or 8 years now, I think. So what we see there is, we run syncoid from the source to the target. We get an informational message that it's sending the oldest full from the source to the target. And we get a nice little progress bar with an ETA. It tells you how fast your data is moving, how much percentage of it you're done with, when it thinks you'll be done, the whole nine.
Yep. So now let's take a look at a couple of the other advantages we haven't really talked about with ZFS replication. The first is end-to-end checksums. So as we know, ZFS stores a checksum for every block that it writes to disk, including its own internal metadata. What's nice about ZFS replication is that we use this checksum all throughout replication. So when we start doing a send, first, before ZFS sends the block, it reads the data off the local copy and checks the checksum and makes sure the data it's about to send is correct before it sends it. And then it sends it along with the checksum so that when it gets to the other side, we verify that what we received is still the correct data. And then we write it to disk. And when you read it back from the backup later, you verify again that it's still the same checksum and the data survived all the way across intact. And if your data is encrypted, there's also a message authentication code in there, making sure that not only is the data intact, but it is not been modified maliciously, because we're verifying that it decrypts properly as well. Another big advantage using replication is atomic updates.
Hang on just one second, Allan. If that was unclear to anybody, what Allan was talking about is that in the event that somebody extremely advanced and malicious manages to modify an encrypted block in a way that it does still actually pass its checksum validation because you've got a hash collision, the Mac makes sure that it will also decrypt successfully, which any random modification that is admittedly clever enough to pass validation because of a hash collision, it's still not going to fly because it doesn't decrypt right. So it's just an extra layer of, nope, that's not right. Try again.
Yeah, it's basically like a checksum, but it depends on having the encryption key to generate. And so someone couldn't generate it with a collision like they could with a regular checksum. Yeah, one of the other big advantages is atomic updates. If you're using a tool like rsync to sync from A to B, then halfway through on B, you now have some newer files and some older files. With ZFS replication, while replication is happening, the incoming data is in a temporary snapshot that's not in place yet, and so it's not visible. So the data on the destination is, snapshot 1 until the second is snapshot 2, and it's never anything in between. It's always the older snapshot or the newer snapshot, never anything in between, meaning that you don't have to worry about accessing the data when it's not fully copied, but also means that once snapshot 2 exists, the replication is finished and successful. You never have to wonder, did the snapshot or did the replication actually finish correctly? It's just either the snapshot's there and it's perfect, or it's not there. There's never anything in between.
This is roughly similar to if you were using a simpler tool like, SCP or what have you. If you were to say, well, I don't want to SCP this new folder into my production folder and have it, be in there in a partial state. So instead, I SCP it to a folder under temp. And then once the SCP completes, I move it from temp to my production folder. What we're talking about with the way the data doesn't really appear at a user perspective, including just a list of snapshots or what have you on the target machine, it's the same concept.
The other big advantage we talked about already is performance. Because ZFS replication just has to look at what blocks changed, it doesn't matter if you have 10 million files and 7 of them changed. ZFS will see, 7 blocks and send them and be done. But other tools, whether it's rsync or regular backup software, is going to have to look at every one of those 10 million files and be like, did you change? Did you change? Looking for files with newer modified dates or different sizes. And to compare sizes, it would have to know what exists on the backup, which means it has to talk to the backup and increase latency there, whereas ZFS never has to do that. And
it also doesn't matter if you're
faster.
It also doesn't matter if you're talking about 30 terabytes of data in a single 30 terabyte file with only 2 or 3 blocks changed. rsync would have to read that entire 30 terabyte file in, serializing it and making checksums and comparing it on both ends. ZFS does not, because ZFS knows which blocks changed and just sends them right over the wire.
Yes, and is unidirectional, like we talked about. It never has to get anything back from the other side. And as we talked about,
once you're actually replicating, although we should point out again, you do actually have to talk to the other side to figure out how to build your replication command to begin with, because you have to know which snapshots are common between the two.
Right. And we already talked about encryption quite a bit. So let's very quickly go through.
Before we move on to permission delegation, I would like to, and I'm probably going to butcher your name. I'd like to address Marine's question. Could you explain a bit about mounting snapshots to get specific files back? Okay, so by default, any ZFS dataset is going to have a special hidden directory called .zfs beneath it. And beneath .zfs, there's a directory called snapshot. And all of your snapshots are listed as directories inside that special directory beneath the hidden .zfs. Now, by default, they're not actually mounted at this point. You can ls them to see all of them, and that's the equivalent of typing ZFS list -rt snap and the dataset name that you're talking about. But when you actually go to enter one of them, a CD or ls of the insides of one of those directories, that's when that snapshot gets automatically mounted into your file system. letting you cherry pick files, out of it as you desire. Now, if you've disabled the .zfs directory or just plain don't prefer to work that way, you can do a couple of things. You can actually mount the snapshot directly yourself. You can just say ZFS mount snapshot name and target, and it will in fact mount it as a read-only file system where you asked it to mount it. You can also, and this is my preferred workflow, whether I really plan on changing much in the data or not, I like to clone snapshots before I work with them. So I'll say ZFS clone source data set at snapshot to data/temp tends to be like my favorite. I'll have just like a kind of a catch-all name that I'll use for clone stuff that I'm just working in for the moment. Once I've done that clone, well, now that's a mounted clone. It's read-write, so you don't have like any weird things going on. Like if you need to use any tools while you're looking at your data that might try to generate new files or more data inside that working set, they're not going to complain because it's a read-write file system. And you can cherry pick things out. You can do things in there. You can work inside it directly, whatever you need to do. And then once you're done, you change directory back out of it, ZFS destroyed, data temp, or whatever you named your clone, and you're good to go.
Yeah, and one really interesting tidbit, in the upcoming OpenZFS 2.2, there's a block reference tree feature, which will mean copying a file from a snapshot back to the dataset. We'll be able to reference the existing blocks in the snapshot rather than having to copy the data, and will make restoring individual files faster.
Oh, that's going to be nice.
Yes.
The other thing that'll be particularly nice about that is if you work with large virtual machine images or something similar to that like I do, it's real tempting when you have a problem like maybe a malware infestation or a user just does something incredibly boneheaded that wipes out a large chunk of the data. You look at that rollback command, you're like, man, it would be so easy just to type in ZFS rollback, pool data set at snapshot, and instantly be back where I was. Now, the problem with that is a destructive command with no undo, and you have permanently destroyed not only what you rolled back from, but also any other snapshots along the way to your target that you rolled back to. So once we've got the block tree going on, then in that situation, rather than rolling back an entire, again, I'll just say 30 terabyte VM image in order to get your RTO down to where you want it, but now you're having to put up with the fact that you destroyed a whole bunch of stuff along the way. Instead, you could use this reflink style copy to just copy the image file right out of the snapshot, have it complete instantly, and you haven't lost your snapshots. Even better yet, let's say this is something like a ransomware infestation or what have you, and you plan to actually address this not just from a sysadmin perspective, but from an infosec perspective later. You want to dig into it and find how did they get in? Can I find out who they are? Maybe can I help the three-letter agencies nail these jerks to the wall? We don't want to destroy evidence. So again, once you've got the ability to ref copy these individual files out without having to brute force copy each individual block, that means you can take a snapshot of your all malwared up system and then do your reflink copy, and just as quickly as the rollback, get back in production without destroying valuable evidence.
Yep. So moving on to permission delegation, in particular, we don't want the backup system we're using to be a source of vulnerabilities in our system, right? We don't want to cause more trouble by having these backups and having a machine be able to come into our production and pull copies of data. So what we want to do there is use the principle of least privilege. So we can make a separate user to do the replications from, and only allow that user to do the things they need to do and nothing else. So you can go ahead.
Go ahead. Okay. All right. At the simplest level, we're just literally talking about ZFS allow username, privilege name, and where you want it allowed. Now, the last argument there, the where you want it allowed, is actually optional. You can just say ZFS allow username privileges, period, and that will allow that user those privileges on all pools and all data sets on the system. But you can also limit it, which can be pretty nice. So perhaps you've got a multi-tenant system. Maybe you're hosting a bunch of things for other people. You can actually separate things out so that you don't have to worry about the backup for user A potentially introducing a vector that might compromise user B, who has nothing to do with user A other than both being your clients. So that's pretty cool. Now, the particular permissions that you'll need for replication, that gets a little bit thorny. The most key permissions are send and hold on the send side and create and receive on the receive side. Now, the other thing I'd like to point out that I think a lot of people missed when these features first started dropping and people first started talking about delegated replication specifically is you don't have to give the receive permissions to the user ID that does the sending or vice versa. And you can limit your exposure quite a bit by making sure that you do actually use separate user IDs to send and to receive with only those permissions granted to them. That makes sure that, for example, let's say that somebody is able to compromise your box with the receive user's permissions. Well, they will be able then to destroy data sets, but they're not going to be able to send them off that box to themselves very easily using ZFS replication, which is, a pretty huge benefit, particularly given that, they're being non-root users. They also, if you've done this vaguely right, won't be able to see the data either, because even if it's mounted, they can't LS it because they don't have the permissions to, because they've got this incredibly neutered user. And from the ZFS side, they can't get the data out either because they don't have send permissions. On the other hand, let's say that somebody manages to get in on your production side. Well, they can send, but because that send user on the production side doesn't actually have a direct counterpart on the backup side, you can't just use that to shell into the backup side and wreak havoc. You also can't do anything but ZFS send to that backup side. Also, if that specific user ID is all you have access to on that production, you can't use it to do anything particularly destructive because you haven't been granted the permissions to. So this is absolutely the right way to do it. It's the principle of least permissions.
Yeah. And if you're interested in this and maybe even taking it further, Klara is currently investigating more fine-grained permissions, especially things like allow destroying snapshots but not data sets, or even allow send but only a raw send, so that the user can only send encrypted copies of the data, not cause it to be decrypted. Both to prevent accidentally sending the data unencrypted, but also to prevent somebody malicious from being able to get a not encrypted version of the data. And lastly, as we promised, we'll talk briefly about resuming replication. So what happens if you're replicating 30 terabytes across the country and your internet connection has a hiccup and you've stopped halfway through? In older versions of ZFS, you'd have to just start over again, and that is not much fun.
Now, I will mention, though, when we say in older versions you'd have to start over again, if you were replicating using that -I flag, the incremental that brings all the snapshots over, one of the neat things is if your replication got broken in the middle, you would have to start over on the specific snapshot you're working on right then, but you would not have to start all the way back over from the start. So, for example, you had automated hourly snapshots and you're replicating the entire stream of these hourlies over to your target, and you lose connection somewhere in the middle of that. You could very easily keep 18 hours worth of your data and only have to start over again at like the 6th hour. Just all depends on where the snapshot breaks. But basically, once your ZFS send completes each individual snapshot in the stream, that individual snapshot is good to go, even if the ZFS send as a whole is still going.
Right. But if in this case, it was if the initial send was interrupted. But
Yeah.
because of the unidirectional nature of ZFS, it means ZFS can't tell how far through the replication the other side was. And so they needed a solution to that. And so for that, what happens on the receive side, a new ZFS property shows up when you have a interrupted replication, giving you what's called a resume token. And that contains what snapshot we were on, which object in that snapshot, how far through that object we were, and allows us to resume that replication. Then out of band somehow, you have to get that information to the send side, which you can do manually copying and pasting, or a tool like syncoid will do it for you automatically. And if we just, for example, take a look, if we run ZFS get the receive resume token, it'll give us this really long string that I truncated because it would have filled the entire slide. But inside that we see, oh, we're sending object 128 at, this offset of 1.5 gigabytes into it. And that we have another 1.5 gigabytes to send. And here's the GUID of the snapshot we're putting it into, and it's called @snapshot. And that's
Now, to be
what the
clear, in
resume
that
token is.
command, ZFS get -H receive _resume _token. Receive resume token is not a keyword there. That's being used as like a file handle. And what you're looking at in the second part of that is what you would get if you did a cat receive resume token. So if you're handling all this manually, is that not correct, Allan?
No, that's literally the name of the property. It's like same as ZFS get.
Oh,
Anytime.
yep. Ignore me. I'm thinking about the other side of this process when you have to actually build your ZFS send command, and we haven't gotten there yet. My bad.
And here it's literally you put -t and then the long string that you got from that thing.
Yeah, but you had to copy all that crap over somehow
Yes.
from the target machine to the source machine and build it into your command,
Mhm.
and that sucks.
Yeah.
But we're going to
And so,
cover why that doesn't have to suck later.
exactly. The next slide's coming up. So yeah, if you just do ZFS send -t for token and put the token, that contains all the rest of the information about exactly where to resume from, and we'll let this send pick up exactly where it left off. And if you want to abort it because you've changed your mind or whatever, on the receive side, if you do receive capital A in the data set, it'll throw away the partially replicated snapshot and allow you to pick up from where you would have normally if you didn't use resume. But as Jim mentioned, you don't have to do all this manually. In this case, he was running syncoid from pool image to pool image copy, canceled it partway through, started it again, and it said, hey, I noticed you interrupted one. I'm going to pick up where I left off, and good to go.
This is why we really, really recommend using orchestration for replication. It doesn't have to be syncoid, but it's a really good idea to use a full-featured, well-established, well-tested replication orchestration tool, because it makes all this so much easier, and it removes so many different ways you can potentially screw up. If you can't think of 10 different ways you could screw up in the process of like completely manually replicating with just the commands from A to B, and something crashed in the middle and you've got to resume it and put in the resume token and everything else, like if you can't already see all the ways that might go wrong, I don't know what to tell you. Whereas if you use a tool that handles all this stuff, automated, then you don't have to worry about it, and you don't have to worry about the million different places that you might accidentally screw up along the way.
Yep. And lastly, as promised, we'll talk about other uses for replication, like data mobility. So sometimes you want to be able to take your data with you. So often when I'm traveling to a conference, I need to take my kind of in-progress source code with me that normally lives on my build server in my home lab. And so I use ZFS replication to just send that entire data set to my laptop, go to a conference for a week, work on stuff, whatever. And when I get home, I just replicate it back to my build server. And now I have that all done. And I kept those in sync without a lot of extra hoops. And especially when we're talking about multiple checkouts of, FreeBSD and ZFS and so on, where we're talking about millions of tiny files, where any other kind of copying was going to be terribly, terribly slow.
Now, with that said, we should point out this is a unidirectional sync. As described, a person replicates their stuff onto a laptop, takes it to a conference, works on the laptop for a week, comes back and replicates it back onto production, where nobody else will have been making changes to it. That is a complete workflow. However, this is unidirectional. This is not bidirectional sync with collision detection and resolution and all that stuff. So don't think this means, oh, this is exactly like a sync thing. It is not. It is essentially an incredibly fast way to copy all of the data from A to B and be certain that you copied it all correctly and intact and no changes and yada, yada, yada.
But, as you mentioned here, one of the big advantages of this is if what I changed wasn't that much, when I replicate back, I only have to send the differences. So if I copied 500 gigs worth of files to my laptop, but I only changed 100 megabytes worth of stuff, then I only have to send that 100 megabytes back.
Jesse asks, is it advisable to run a scrub on the destination pool after a send or receive? And the answer is no, you really don't need to do that because the process of receiving itself validates all those checksums while it's happening. So running another scrub immediately after, I mean, it's not going to hurt anything, but there's not any particular point to it. The better answer is your destination should be getting automatically scrubbed on a regular basis anyway. And whenever the next regularly scheduled scrub comes up, that's fine.
But yeah, as Jim alluded to, on the receive side, it's checking the checksum of every block it receives before it writes it to disk, because it wants to make sure what it writes to disk is exactly what was sent from the other side.
And B. Folus asks, can replication work with disk rotation in a situation where you want to have multiple offsite physical disk backups? And the answer to that is absolutely. To simplify, we'll say that you've got, let's say maybe less than 12 terabytes of data. So you can easily fit everything that you need onto a single, if relatively large, Rust drive. So what you would do for your offsite rotating disk backups is in your server that presumably has hot swap bays that are easily accessible so you can slap drives in and out of them. You would set each one of those hard drives that you plan to take offsite up as single disk pools. So you import your single disk pool for the Monday backup. You run your replication task with it as the target. You export the Monday disk's single disk pool, and then you can just pull the drive out of the system, take it offsite. The next day, you slap in the Tuesday disk, lather, rinse, repeat.
Yep. And that way you have multiple different things. You can also daisy chain replication. So you can send from A to B and later send from B to C. But if B dies, you can still send directly from A to C or even C to A. Because you're just sending snapshots, as long as you have common snapshots, you can send in any direction you want.
With that said, given that we're talking about replication and given how dramatically lower the load on both source and target systems is with replication compared to traditional tools like rsync, I don't generally recommend an A to B to C schema. As Allan said, it absolutely does work, and if you need that in order to reduce the storage load on A, you can. However, what you've done is introduced a single point of failure for what's supposed to be a redundant backup solution. Because if B dies, C stops getting backups until you deal with it. So it's almost always better to do A to B and A to C rather than A to B to C.
Yep.
And so, really, technically, I want to say also, I said A to C, but in reality, it's almost always better for C to pull the backups from A rather than A pushing them to C. Because your backup system should be the most secure system you have. You don't have to give anywhere from, a couple to maybe even thousands of users any kind of access to it. All it has to do is pull the backup. So it's a much harder target. And that's why it should be the one pulling the backups from A. So A has absolutely no access whatsoever to C, the backup system. C reaches out to A, pulls the backups, disconnects from it, and that's it. That's the safest way to go.
Yep. If you want to use ZFS replication and need some help with it, you should check out the Klara OpenZFS support subscription. This gives you access to our team of experts, administrators, and developers to help you answer your questions, maintain your storage, get your replication up and running and keep it running, and resolve any issues you might encounter. If you've not started using ZFS for your storage array yet, you should check out our design and implementation solution, where we will help you pick the best hardware and build out your system and set up a good backup rotation and define your RPO and RTO and everything to get you running with ZFS.
Okay, Marine, and I apologize if I've butchered your name again, asks, can you do a ZFS bull? I only know ZFS send. So if you're using the raw commands, what a ZFS pull is, it's a descriptive term. It's not a command that you run. And the way that would work is you say, okay, from my target system, I SSH into my source system and tell it to do a ZFS send command, which I then pipe back to myself into a local ZFS receive process. Now, if that broke your brain a little bit, don't worry about it. Just don't try to use the commands raw. Instead, use a tool like syncoid. Syncoid just handles all that for you. Again, if you say syncoid remote machine, local machine, well, it's just going to reach out and do that for you. Matter of fact, it will even let you replicate a remote source to a remote target from a machine that sits in the middle if you want to do that for some reason. By the way, if you do actually need to do that for some reason, I'd love to hear from you. I built that feature in from day one of release of that tool, thinking somebody somewhere would probably want it. I don't know if anybody ever has, and I'm curious. I know I never have. Anyway.
Yeah. So basically, the point is the cron tab should run from the backup machine and cause things to happen rather than the primary machine having the ability to reach over into the backups. Okay, great. I think that's we're at time. We hit the top of the hour. So thanks everybody for coming, and thanks again, Jim, for joining me.
Bye, everybody.